to 5. GLUT1, GLUT2, GLUT3, GLUT4, GLUT5. Okay. GLUT4 is for adipose tissue and skeletal muscle. So that uses GLUT4. So these two tissues, adipocytes and skeletal muscle, uses GLUT4 so that glucose can enter. Okay. All right, so we have here types of GLUTs, no? This one is, you are of course familiar already with this term, symport. Glucose comes in together with sodium. Okay, that is a symport. Now, if it is only one, that's a uniport. And you know what is this? This is an antiport. Sodium gets in, this one, potassium goes out. So no sodium can get in unless potassium can go out. Or no potassium can go out unless sodium can come in. Okay, so these two are dependent upon this sodium potassium pump. Dependent, because as you can see, this one requires sodium together with glucose to come in. So if you are putting out the sodium out, you're putting out the sodium, then sodium now comes in with glucose. Okay. All right.
Glucose follows sodium across the lumen and sodium
Endocytosis and exocytosis. Okay, for these are large molecules, so macromolecules, like polysaccharides, proteins, polynucleotides. Okay. Endocytosis involves ingestion of parts of the plasma. Sometimes endocytosis is also called cell drinking. The cell is drinking. Okay. All right, so we have it here. As the extracellular space, this is your membrane. Then there is invagination. And the cell membrane, the opposing cell membrane here, will close that one until once they are joined together, this is going in. Now, look at that. So, endocytosis, ingests part of the membrane. So part of the membrane here. So you see the membrane here. So part of it is ingested. Okay. There's another form, because this is known as fluid phase pinocytosis. And the other one on the other side, this one here, absorptive receptor mediated endocytosis. Now the thing here is that the invagination the invaginated portion has proteins like a brush. These are what you call your clathrin proteins. Clathrin. Where is that? Oh, here. Protein clathrin. Okay. So, again, as part of that, similar to this, they are going to join together, and then you have a vesicle lined with clathrin proteins. There. So that is your cell drinking or pinocytosis. Now, exocytosis releases certain macromolecules from cells. Most cells release large molecules outside. So this is through exocytosis. Oh, here is a comparison between exocytosis and endocytosis. So these are the molecules that has to be extruded out of the cell, and then it has a membrane very similar to that, so that it will join. Look at this. It will join the membrane and then extruding out what it contains. So that is the opposite of where is that? Okay, so this is the opposite of invagination, where it forms a vesicle and then you still have the membrane here. Now this one is you are the molecules to be extruded out has to be inside a vesicle in which the membrane of that is similar to the membrane here. Your cellular membrane, so that this membrane that encloses the macromolecules can become a part of your cell membrane. Okay. Now this is endocytosis. Membranes here, the same membrane. And this pinch off, and this forms now. Of course, this will open up where it is utilized, the molecules inside. And what happens to the membrane here will be degraded into phospholipids, fatty acids, amino acids, and will be material used again for forming membranes in here. So that you'll have the same material for this envelope or enclosure, so it can join your cellular membrane. You get that? Okay. Molecules released by this mode of exocytosis have at least three fates. They are membrane proteins and remain associated with the cell surface. As it is there, becomes part. They can become part of the extracellular matrix, for example, collagen and glycosaminoglycans. this one here can be part of glycosaminoglycans. They can enter extracellular fluid and signal other cells. Insulin, parathyroid hormone, and the catecholamines are all packaged in granules and processed within the cells to be released on appropriate stimulation. Okay? And of course, the opposite, the materials from the outside getting inside will be utilized. This could be glucose, this could be amino acids, short peptides. Okay. Various signals can be transmitted across membranes. Signals such as neurotransmitters. So there are molecules that can act as neurotransmitters. And then, of course, hormones and immunoglobulins. They bind to the integral transmembrane receptor proteins, and they can become transmembrane signaling, signal transduction. Okay, let's look at this. Gap junctions. What are these gap junctions? Now, in between cells, two adjacent cells, they can exchange materials through gap junctions. Now, imagine you have two cells near each other, and imagine that there is a pipe from one cell to another. So this pipe from one cell, materials from one cell can go to the other cell, or from the other cell towards to this cell here. No? Okay. And this gap junctions is formed by connexins, forming a bihexagonal structure. Bi meaning two hexagonal structures. So there are 12 structures, and that structure are proteins. So 6 connexins from one cell, and another 6 connexin from the other cells. Okay, and then they form a gap junction. The pipe that I was telling you, so it could be a pipe. So here it is. Here is one cell, and the other one down here. Okay, so there are two cells. This is only just a portion. So these are your gap junction. You notice from one gap junction to the other gap junction, it looks like a tube. Diba? Looks like a tube. So here you are. This looks like a flower. So here are your connexins. This is 1, 2, 3, 4, 5, 6. And on the surface of another cell, you will also have this. So there are 6 here, another 6 here. That makes it 12. And they form a connection. So materials coming from here can go in here, and materials from here can go there. But that does not mean that is always open. No? This is regulated. Now, look at this. This is open, and look at what happens to that. So there is a movement. So when it moves a little, this one down, this portion goes up. So this one also. So you will have now an opening. And then this closes. Okay? So we have here open and close complete connection channels, the flow of molecules, blue, red arrows. So there's a red arrow there. No? One connection is made from two hemiconnexons. Each hemiconnexon is made from 6 connection molecules. Small solutes are able to diffuse through the central channel when open, thereby providing direct mechanism of cell-to-cell communication. So they can communicate here. Their communication might be just fluid or some solutes or materials that is needed, or it could be a molecule that signals activation of the cell. So it also signal that one there. And this cell has also a connection to another cells so that that tissue could be stimulated or inhibited. It depends on what molecule passes through, whether that molecule can stimulate or can inhibit. Okay. Extracellular vesicles or exosomes represent a novel and previously underappreciated mechanism of cell-to-cell connection. Okay. Now here, this does not use the gap junction, but rather cells produces some materials that can be utilized by another cell, no, through kinds of receptors, like this one. This is the cell, source cell. The source will produces these materials here, also some materials, and then we have different receptors. So we have different receptors. So supposing this one here attaches itself, and this is an antigen. So these are different materials, no? It depends now on what surface or what receptors will they bind, and corresponding reaction of the cell once they bind to the receptor. Okay, so depending on the target cell, whether those materials are hormones, antibodies, so it all depends on also on the target cell. Okay. Mutations affecting membrane proteins cause diseases. The diseases, of course, that are formed here are not common. They're not common. Okay. Due to mutations. So here are the diseases. Okay. abnormalities. Abnormalities. Okay. Familial hypercholesterolemia. So meaning to say, there is a problem with the LDL receptor. So the LDL could not be taken in by the cells because the receptor for LDL, there is a problem so that the LDL cannot bind to that receptor. So what happens? LDL will be roaming around in the plasma. And what does LDL carry? Cholesterol. So that is what we call familial hypercholesterolemia. Familial because it is genetic. And the problem is the receptor. The receptor here cannot bind to the LDL, which carries cholesterol. You get it? Now? So all are mutations. All are mutations. And as mutations, mutations are not common. Okay, so familiar. Usually, if the father has this mutation, the mother has also this mutation, naturally, the offspring has this mutation. Okay? Oh, continuation. No? So, hereditary spherocytosis. This is your RBC, which is involved. Metastasis of cancer cells. Nocturnal hemoglobinuria. Nocturnal hemoglobin. So you are urinating hemoglobin. Okay. So these are, as we said, these are not common. No. Now, like for example, cystic fibrosis. There you are. This is common in North America and Northern Europe. No? Both of these countries have cold winter. Very cold. No? And what does that got to do with mutation? Cold countries. Families are usually sleeping together. In order to preserve the warmth of their body. And what happens? Incest is common. Okay? Another thing is Europe, usually, yes. In Europe, it is customary there to marry within the family. And so this brings about the recessive gene becomes dominant when the male and the female both have recessive genes, their offspring, usually that recessive gene becomes dominant. Okay? Because it is customary there, no? Like, you know how it is. To preserve the kingdom should not be divided. Diba? And so that the kingdom will not be divided, then they marry within their family. Okay. So that is not happening with us. No. So, kadagan baning thank you. Sama to. 13. Oh, battery running low. Okay. Let's go to chapter 11. The role of ATP, bioenergetics. You are familiar with ATP, diba? Okay. Okay, biomedical importance. Well, this has got to do with nutrition, no? Because it says here starvation, marasmus, metabolic rate, obesity. No. Now, all of this has a common ground, and that is energy. Less energy, as in starvation, okay? And in malnutrition, less energy gap. And then, of course, plenty of energy, obesity. Where do you get your energy? The food that you eat. Okay. So in starvation, there's no food. In marasmus, there might be food, but the wrong kind of food. That is taken in marasmus. It's energy imbalance as well as protein, no? Imbalance. And then obesity, there's plenty of food. So there is surplus of energy because there's plenty of food. Okay. So let's start there to understand this. Energy procurement. Gibbs was the first one to coin this free energy change. This free energy change is named after the researcher Gibbs. No relation to Jano Gibbs. And this is the symbol for free energy change, delta G. Okay. All right. That free energy change is that portion of the total energy change in a system that is available for doing work, or that is what we call useful energy, also known as chemical potential. Okay. First, we must have to understand these laws of thermodynamics. Let's borrow these two laws from the engineers. Uh, so the first law of thermodynamics states that the total energy of a system, including its surroundings, remain constant. Okay. So what do you mean by the system? The system includes you, all around you, or the entire Philippines, or the entire world, or the entire universe. That's the system. So if you go micromolecular, from the cell, surrounding the cells, or anything that surrounds the cell, or its environment, is the system. Or you want to be astronomers, Earth, together with the planets, or with the solar system, that's a system. And the solar system, our own solar system, is just only a portion of the universe, which that is included as a system. Yeah? Now, when I was still a student, when we were talking about energy, and our professor once told us that, oh no, ask us, how do you define God? No one could answer. How do you define God? And then we asked him, how do you define God? And he said, God is energy. Because everything is energy. No? Okay. Energy has no origin. No? Cannot be created, cannot be destroyed. But it can be transformed from one form of energy to another. Diba? So, I've read a definition of God. It says God has no beginning and has no end. So it is just like energy has no beginning and has no end. The energy that you can easily see, can feel, or you're aware of, and you have plenty of that in Leyte, is the electrical energy from Tungunan. Diba? How was the electrical energy made in tungunan? It comes from thermal energy. And what is the thermal energy in tungunan? It is volcanic steam going out from the bowels of Earth. And that thermal steam is used to drive a turbine. And when the turbine turns, it turns the generator, electrical generator. And the generator forms electrical energy and is distributed by transmission lines, and it reaches Tacloban, and there you have electricity. So that electrical energy can be transformed into light energy as the source of light, or it can be converted to thermal energy as your electric stove. Diba? Okay, so you have now understanding of what energy is. And the first law of thermodynamics says that the total energy of the system, including its surroundings, remains constant. It is there. Okay. All right. The second law of thermodynamics that we have to understand is that the total entropy of the system must increase if a process is to occur spontaneously. What is entropy? Entropy is a state of disorderliness. State of disorderliness. So if you increase the disorderliness of a system, now increase, a process is to occur spontaneously. So how can we, okay. We are not having a class where you are seated down. And then just imagine that you have a class there. You are seated down. You have your teacher in front of you. And because he's very strict, you do not even move in your seat. And you just listen to him. No? So that is an ordered entropy. You are all sitting down doing nothing, just listening to your teacher. That's an ordered entropy. All of a sudden, somebody shouted from the outside and he says, "Fire! Sunog!" So everybody stands up and then rushes to the door. That is now increasing the entropy. You increase the disorderliness. There's so much disorderliness that you bump into your chairs, you bump into each other. So it is just like molecules in a chemical reaction. The molecules that is not disturbed, it's in entropy. Now, you must have seen this in your kindergarten chemistry, that if you want to hasten the reaction, you try to heat it in your Bunsen burner. No? Diba? So heat there increases the entropy of the molecules. The molecules gathers energy and it moves around. And we said no chemical reactions can occur if the molecules will not collide. collision theory. Diba? Ah. So, if you increase the entropy, a process is to occur spontaneously. So if you have two molecules who have high entropy, then they just chemical reaction can occur spontaneously if they have high entropy. Right? Yes or no? All right. So let's try to, look at this. Under conditions of constant temperature and pressure. So under condition of constant temperature and pressure, you're not increasing it, you're not decreasing the temperature and the pressure also. The relationship between the free energy change of a reacting system and the change in entropy is expressed by the following equation. So free energy change is delta G. Delta H is change in heat or enthalpy minus temperature, absolute temperature, times delta S. S is entropy. So, free energy change is equal to change in enthalpy minus temperature times change or delta S, no? Change. Once you say this delta, it means change of entropy. But the problem of this is, how can you measure disorderliness? How can you measure disorderliness? All right. So let's go to the next one. Delta H is the change in enthalpy, and T is absolute temperature. In biochemical reactions, delta H is approximately equal to the change in internal energy of the reaction. My God. So we change delta H to delta E because that is approximately equal. Change in heat is equal to the total change in internal energy or delta E minus absolute temperature and change in entropy. Okay. Now, let's go to what we call, again, let's go back again. We cannot measure this. So what are we going to do? We go to this one. So the standard free energy change can be calculated from the equilibrium constant of the reaction. Okay, so this is standard free energy change. So you get this superscript, that means standard free energy change, where R is the gas constant, T is the absolute temperature. Normal logarithm of your KEQ, which is a constant, equilibrium constant, KEQ. R gas constant, T absolute temperature. All right. So these are all measurable. So we use this because we cannot do this because we cannot measure disorderliness. All right. So if what comes out, if delta G is negative, the reaction proceeds continuously with the loss of energy. We call such reaction as exergonic. On the other hand, if delta G is positive, the reaction proceeds only if energy is supplied to it. And we call that endergonic reaction. When the magnitude of the positivity of delta G is high or great, the system is stable and there is no tendency for reaction to occur. If delta G is 0, then the system is at equilibrium. Okay? Out. We have here an exergonic reaction, which is from point A going to point B, is what is called a downhill reaction. Going down. There. Endergonic reaction is an uphill reaction. Uphill reaction. So this is the analogy, no? Now, exergonic reaction, okay, just like going downhill, you don't need energy. Just go that way. And endergonic reaction requires energy to go uphill, right? Okay. In our system, our cells, endergonic reaction, a reaction that requires energy, usually couples with exergonic reaction. Meaning, whatever energy that is released here will be used to propel the endergonic reaction to occur. Okay? As you can see, there's a difference. It does not, this endergonic reaction does not go up there. No? But this is only up there. So in our cells, there is a coupling. Endergonic reactions, these reactions is coupled to exergonic reactions. Exergonic reactions. Releases energy, and the energy is used up for this reaction to occur. And there's a discrepancy, look at that. And that is released as heat. Now, going back to the body, this heat released in your system is used to have your body heat, which is 37 degrees centigrade. So that's the remnant of the energy released here and used up. Not all of the energy released used up by the energonic reaction. The remainder is body heat. Okay, get that, no? All right. But it does not mean that endergonic reactions will have to wait for exergonic reaction to happen. It is not meant that way. Now, it does not always mean that if you have exergonic reaction, you will also have endergonic reactions. No. Exergonic reactions are always happening, and the energy that is released is captured for use when it is needed when an endergonic reaction has to occur. So there is a capture. Energy released there is captured, and then for later use or future use for an endergonic reaction to occur. Okay. All right. Here is an oxidation reduction reaction shown here. Okay. We have a compound which is a reduced compound. Compound A is a reduced compound. It is oxidized and it loses your hydrogen. The acceptor of that hydrogen is another compound which we call a carrier, and the carrier now has this hydrogen. And this hydrogen has a final final acceptor of hydrogen is compound B. And B accepts the hydrogen. This is oxidized compound. And then once it acquires the hydrogen, it becomes reduced, BH2. All right. Now, it does not mean that you have only one carrier. There might be another carrier before a final acceptor of hydrogen comes around. Now, this is an example of an enzyme or dehydrogenase. D meaning remove, hydrogen, ASA means enzyme, no, dehydrogenase. So coupling of dehydrogenation and hydrogenation reactions by an intermediate carrier. So this is your intermediate carrier. Okay. So compound A, which is reduced, becomes now compound A oxidized. So oxidation meaning loss of the hydrogen here. Diba? And the gain of hydrogen makes the compound B, which is oxidized, becomes now reduced compound B. Okay? All right. And if you remember, let's go back again. We said every exergonic reaction that occurs, the energy is captured, no? Being captured to be utilized for endergonic reactions to occur. Okay. What captures that energy is this compound, which you are familiar with, ATP. You have here adenine, which is a purine. You have ribose, which is a sugar. And then you have 3 phosphates. This bond between this carbon and this carbon is an ordinary ester bond. Okay? But this bond here, from phosphate to phosphate, phosphate to phosphate, you have anhydride bonds. Anhydride bonds. When you cut off this bond, you release energy. Or you cut off this bond, you release energy. Now here is your magnesium stabilizing these two. So this is what we call your energy currency, ATP, and its cousins, because you have cousins. You have your GTP, you have your TTP, you have your CTP, UTP. Okay. But ATP is the one that does most of the job in storing energy here. Now this is a table for high energy phosphates. Okay. Where is your ATP? It's here. When ATP releases one phosphate, it produces 7.3 kilocalories per mole. If the 2 phosphates are removed, you have 7.7 kilocalories that is released. See, now this one is kilojoules. No? But we are mostly using kilocalories. Okay. So the highest here is phosphoenol pyruvate with kilocalories of 14.8 or 14.7. Carbamyl phosphate has 12.3. 1,3 biphosphoglycerate, you have 11.8. Creatine phosphate, 10.3. Okay, and so you have your ATP losing 2 phosphate, 7.7. ATP losing 1 phosphate, 7.3. Below that, below your ATP are now considered as low energy phosphates. Low energy phosphate. Glucose 1-phosphate has only 5. Pyrophosphate removed from ATP is only 4.6. fructose 6-phosphate is 3.8, glucose 6-phosphate is 3.3, glycerol 3-phosphate is 2.2.